Hello everyone, I'm Kamal. Today I'm going to talk about our work named Not All Attributes Are Created Equal, DX Private Mechanisms for Linear Queries. This is a joint work with Victor, Hassan and Dali. Let's begin with a well-known formal notion of privacy called differential privacy that allows a trustworthy data curator in possession of sensitive data from several individuals to approximately answer a set of queries submitted by an analyst while maintaining individual privacy. Here the dataset is denoted by X, query by Q, and the privacy mechanism by M. A differentially private mechanism does not distinguish between neighboring datasets when answering a query. The neighboring datasets are the ones that differ in one row or in the data of one individual. The privacy mechanism outputs a randomized response to the query by injecting carefully calibrated noise to the true answer. Formally, a mechanism M is epsilon differentially private if for all the neighboring datasets X and X dash and for any query Q, the randomized responses vary only by a multiplicative factor of the exponential of epsilon. Here, epsilon is called the global privacy budget. One limitation of this definition is that it provides same level of protection for all the attributes of the dataset. In many scenarios, a more flexible notion of neighboring datasets may be more useful. For instance, in some domains, it might be more natural to measure the distinguishability between two datasets by some generic metric dx defined on the data universe X. Here, dx satisfies the properties of a metric such as non-negativity, symmetry, and the triangle inequality. With this generalized notion of neighborhood where dx metric, we say that a mechanism M is dx private if for all the neighboring datasets X and X dash that differ only in the I, jth entries, the randomized response for any query Q vary only by a multiplicative factor of the exponential of the dx distance between ith and jth elements of the data universe. Here we have a separate privacy budget for each pair of elements in the data universe. Now we look at some use cases for the DX privacy notion. In location-based systems, it might be acceptable to disclose coarse-grained information about an individual's location instead of his or her exact location. In this case, the geographical distance would be an appropriate measure of distinguishability. In the experiments, we'll consider this use case. There are other scenarios where some attributes of the data set may need more protection than others and vice versa. As an example, consider a classification problem with instance space X where specific features of X are more sensitive than others, maybe due to fairness requirements. In this case, it might be reasonable to choose a metric with differential privacy budget epsilon i's for different features. In both cases, the global privacy budget compromises much in the utility. One common mechanism for achieving differential privacy is to inject random noise to the query answers and sending a random response to the analyst without compromising much on the utility. The injected noise is carefully calibrated according to the sensitivity of the query and a global privacy budget epsilon. Sensitivity here is defined as the maximum amount of change in the query answers corresponding considering all neighboring datasets, which means datasets differing in the data of one individual. The Laplace mechanism adds a noise distributed according to the Laplacian distribution with a scale given by sensitivity divided by the global privacy budget. Note that lower the epsilon, higher the noise added and compromises much on the accuracy. One can directly adapt the Laplace mechanism to satisfy dx privacy by choosing the global privacy budget epsilon to be less than minimum of all the pairwise dx privacy budgets. But this would compromise much in the utility. In this work, we propose a systematic approach to convert any epsilon differentially private mechanism into dx private mechanism while maintaining high utility in the response by exploiting different pairwise dx privacy budgets. Before delving into the technical details of our generic strategy, we will start with a working example. Consider a simple domain with three binary attributes, gender, native, and age. We assume that the attribute value native equals y is considered sensitive and all other values are non-sensitive. Since we have three binary attributes, there will be 8 elements in total in the data universe. We denote them by x1, x2 up to x8. For instance, x1 represents an above 18 native male. This figure shows an example dataset X as a histogram from this domain. Now we want to respond to some sensitive and non-sensitive queries on this dataset. First, using differential privacy, the data custodian might wish to use some privacy budget epsilon 0 for the sensitive attribute value y and infinity for all the other attribute values. Note that the privacy budget of infinity corresponds to not adding any noise to the query answers. Any linear query Q with non-zero value for coordinates 1, 2, 5 or 6 will be answered with budget epsilon 0 since these coordinates contain the sensitive attribute value y. All remaining queries are answered with a privacy budget of infinity. Even though this sounds like a reasonable strategy, considering a linear query that has ones in the coordinates corresponding to the attribute value n and zeros elsewhere, this query corresponds to the number of non-native people in the data. Using the above strategy, this query would be answered with a privacy budget of infinity. Since the number of entries in the dataset n is assumed to be publicly known, one can get noiseless answer to the sensitive query that has ones in the coordinates corresponding to the attribute value y and zeros elsewhere. This query corresponds to the number of native people in the dataset. This example shows why attribute-wise privacy budget allocation should obey the properties of a distance metric. We can solve this issue by using dx privacy. First, we set the privacy budget allocated to the sensitive attribute value as epsilon 0 and privacy budget for any other attribute value as epsilon 1. Here, epsilon 1 is greater than epsilon 0. We denote any element xi in the data universe by a tuple of three attribute values xi superscript 1, xi superscript 2, and xi superscript 3. Finally, dx distance between xi and xj is defined as follows. We take the minimum of the corresponding privacy budgets when there's a mismatch between the attribute values of xi and xj. For instance, dx distance between x1 and x2 is epsilon 1 and dx distance between x1 and x3 is epsilon 0. One can easily verify that this is indeed a distance metric. Given any linear query Q, one way to answer through our framework is to add Laplace noise of scale C given by this particular formulation to the answer. In the following slides, we will discuss how we derive this noise scale. Thus, for instance, for the linear query that has ones in the coordinates corresponding to the attribute value n and zeros elsewhere, we get C equals 1 over epsilon 0, which results in adding high noise to the query response. We have already seen that this is indeed a sensitive query and is equivalent to answering the query the number of native people in the data set. Thus, the noise scale is justified. Now consider a linear query with ones in the first four coordinates and zeros in the remaining coordinates. This query corresponds to the number of males in the dataset and it is not considered sensitive. For this query, we get C equals 1 over epsilon 1, thus less noise is added to the answer to this query. When epsilon 1 goes to infinity, we can even get noiseless answers to the non-sensitive queries. Recall the Laplace mechanism. To achieve epsilon differential privacy, we compute the difference in the answers to the query over all neighboring datasets given by the global sensitivity delta, and then add the noise of scale delta over epsilon. The corresponding quantity in dx privacy is pairwise sensitivity delta of I, j divided by pairwise privacy budget dx of I, j. But this is potentially different for all I, j. Therefore, to obtain a dx private counterpart, we need to obtain a single optimum noise scale C. For this purpose, we consider two model parameters, noise scale C and transfer query Q dash, which is approximately equal to original query Q divided by C. Then our generic strategy is a two-step process. In the first step, we obtain the model parameters C and Q dash for a pre-processing optimization. We will discuss the details of this in the following slides. In the second step, we replace the output rule of epsilon differentially private mechanism with a slightly modified output. Here Q of x is replaced by C times Q dash of x, but they are approximately equal and noise is C now. One can easily verify that the resulting mechanism is dx private if the pairwise sensitivity of the transfer query Q dash is less than or equal to the corresponding pairwise budget privacy budget. The model parameters C and Q dash are chosen by approximately solving a pre-processing optimization problem with an objective function that acts as a surrogate for utility measure that we are interested in. The constraints of the optimization problem capture the DX privacy requirements. The exact form of the optimization depends on the utility measure and the DX metric under consideration. In general, these problems are non-convex and computationally challenging, but we show that for certain loss functions, the optimization problem can be approximately solved using heuristic approaches. Note that this pre-processing optimization depends only on the data universe X, the query set Q, and the database size N, but not on the dataset X. Thus, we don't compromise any privacy during the optimization procedure. We experimentally evaluated the effectiveness of our framework on both synthetic and real datasets. The datasets considered in these examples are geographic in nature. More specifically, the data universes considered consist of points in the Euclidean space which allow an intuitive Euclidean distance based on dx metric. Under this metric, fine-grained location information is protected while larger regions provide better utility. When dealing with geographical locations, it might be acceptable to disclose the region of an individual. On the other hand, disclosing the precise location of the individual is less desirable. Thus, it is useful to have distinguishability level that depends on the geographic distance. In the experiments, we compare the performance of standard epsilon differentially private Laplace mechanism with epsilon equals the minimum of all the pairwise dx privacy budgets and our dx private Laplace mechanism. We generate a random dataset with 10,000 records and a data universe of size 50. We then randomly sample capital N distinct two-dimensional points ui, vi's from 100 by 100 grid and associate each point with an element I of the data universe. The sample data universe elements are shown in the figure. We then define the privacy metric based on the Euclidean distance on two-dimensional space. We measure the individual performance of the mechanisms by root mean squared error between the private response and the actual output on the above generated data. We define another measure of for cross comparison of the two mechanisms. For a given single linear query Q, the improvement factor of the dx private Laplace mechanism compared to the baseline epsilon differentially private Laplace mechanism is defined as shown in this formulation. This factor is simply the ratio between the scales of the noise added by the two mechanisms. Likewise, for a given multilinear query Q, the improvement factor is defined as the geometric mean of individual improvement factors. For a single linear query Q, the model parameters C and Q dash of the dx private Laplace mechanism can be obtained by solving this pre-processing optimization problem. Here, the objective function is chosen by doing a utility analysis for our mechanism with L2 scared loss function and by fixing CQ dash equals Q for very large n. Then we obtain the model parameter values as presented here. Recall that we used this noise scale in our working example before. We evaluated two mechanisms over 1000 random single linear queries where the query coefficients are randomly drawn from a uniform distribution over the real interval between 0 and 1. Then for each random query, we compute the improvement factor. The resulting values are presented in the histogram form in the figure. The dx private mechanism exhibits significant improvement in utility compared to the baseline mechanism. Next, we consider multilinear queries given by K by N matrix Q, where we vary K from 1 to 10. We consider the same data privacy metric and performance measure used in the previous experiment. Now, the model parameters for our dx private mechanisms are k-dimensional noise vector C and K by N transferred matrix, query matrix Q dash. The values for the model parameters are obtained by approximately solving this pre-processing optimization problem. Note that the constraints correspond to the dx privacy requirements and the objective function is derived from a utility analysis of the mechanism. We consider three different strategies to choose a noise vector C for a fixed choice of Q dash defined above. In the first strategy, we treat the multilinear query as K separate single linear queries and share the privacy budget equally between the queries. In the second strategy, we add same scale noise to all the query response components. In the final strategy, we obtain C via a new algorithm called parameter selection algorithm. This distributes the budget between queries proportional to the privacy budget requirements. Note that all three strategies lead to a feasible solution to the pre-processing optimization problem. We consider two types of query matrices. The first type consists of matrices whose entries are drawn from a uniform distribution over the real interval 0 and 1, and between 0 and 1, and the second type has matrices whose entries are random binary numbers 0 or 1. For each k from 1 to 10, we randomly draw 100 query matrices q of size k by n and compute the averaged improvement factor for the above three different choices of key C. The results are shown in the figures. Strategy 3 outperforms other strategies for both types of query matrices. This is understandable as this strategy uses a smarter way of allocating budget between queries. More significantly, this strategy performs much better for the query matrix with binary coefficients. Strategy 1 has only a marginal gain for binary coefficient query matrices. Next, we empirically evaluate the DX privacy mechanism for random single linear queries on a real-world geolocation dataset with longitude, latitude, and elevation attributes. The dataset is based on the United States cities database, which contains location and population count of the cities in the United States along with other details. From this dataset, we extract the location and population count of the cities with more than 50k inhabitants and resulting in total of 741 cities. We further augment this dataset with elevation information by querying the Google Maps elevation API with corresponding latitude and longitude values. We translate this dataset into a histogram over the cities with n equals 741. The 2D locations of the towns are shown in the figure. We define the DX privacy a DX metric based on the Euclidean distance on the 2D representation. We generate and evaluate 1,000 random linear queries over this dataset. The improvement factors of these queries are shown in the figure. The average of improvement factor values lies between 2 to 3, with some queries showing an improvement factor of more than 7.5. We also tested the improvement factor over the queries with an obvious real-world interpretation. One such query is the average elevation of a US resident's house. In this case, our algorithm performed particularly well with an improvement factor of 202. This scale of improvement is due to the fact that there's a strong correlation between the query and the distance map. Note that even if the solutions shown above are suboptimal, we still perform better than the baselines for both synthetic data and the real data depending on the query structure. Finally, I end the talk by noting other extensions discussed in our paper. In the experiments, we have also considered blowfish privacy without constraints. We have also discussed about the heterogeneous privacy for tabular data. We also derived DX private counterparts of exponential mechanism, small db, and MWGM mechanisms as well. Finally, we have also discussed efficient ways of solving the pre-processing optimization for statistical queries which exhibit some specific structure in its form. Thank you.